Hello? Okay, good. Xiaoyi from Ohio State University. Okay, so today the talk I'm going to present here is about deep learning over big data. So for some of you may be familiar with our work during the last several years, we typically give a talk like high-performance big data computing over HPC clusters or with HPC technologies. So because of deep learning, so we have to move ourselves to deep learning stacks. And so today the talk will be a little bit different. Okay, so why deep learning is so hard? I think there's three major pillars to make it very useful and powerful. Okay, the first one, of course, let's thanks to the deep learning scientists to make a very good model which has very good accuracy to do a lot of wonderful jobs. And the second thing is data. We have to thank everybody because every day, whatever we did on in the internet or with our cell phones, we make data. Okay, and also those data is helping deep learning models get trained better and better. And then the third thing is like HPC guys, whichever they're trying to develop a lot of new advanced technologies to give a very high compute and communication and storage capabilities, which all these three pillars make it deep learning become a very, very useful tools. Okay, so before I talk the technology, let's give an example. Okay, why deep learning? What kind of scenarios deep learning can be used in the industry or in many of the companies? So this is one example coming from Yahoo Flickr. I think what this application does is actually they're trying to automatically do the photo filtering. Okay, so for example, you have a lot of pictures in your cell phone. You can do it. You can manage it by yourself. Just click. Okay, this one belongs to this tag. That one belongs to another category. That's doable by yourself. That's because you only have like thousands of pictures, something like that. But if you look at the Flickr perspective, they need to manage so many pictures, right? Millions, thousands of millions of pictures from all the users. So how they can do this manually? That's impossible. So you have to develop some tools to make this process automatically happen, right? So they are using deep learning technologies to automatically categorize all these pictures into under different tags. So behind this thing, actually, what kind of technology they are using? So we call this deep learning over big data pipelines. So think about why this pipeline is so important. Okay, so because typically we are talking about deep learning, we only talk about training or inferences. Actually, if you look into the business pipeline or workflow perspective, there's a lot of work which are non-deep learning work. Look, you have to prepare your data to some format before you feed into deep learning framework, right? And then you run some deep learning jobs, and then after that, you definitely have other algorithms or other stage which are actually not deep learning jobs. For example, you want to do some query, right? There's a new trend like people trying to combine SQL and the deep learning together, right? And then the last thing is, for example, after you have the model, you have some training data, you actually want to use this model in your business. Then you have some new incoming data, right? It's like streaming data comes, and then you have a model. Now you need to combine this together. So this actually is the whole pipeline in the real scenario, okay? Now the question is how to make this whole pipeline as efficient as possible. Basically, there are two ways, right? One way is, okay, you have one big data dedicated cluster. Then you set up another cluster to do deep learning, like you run TensorFlow or your Caffe over there. And then now you have another tools, make these two flow come together, becomes a real business environment. That's actually wastes a lot of resources. Now the question is, can we combine deep learning and big data together, make them a unified stack? That's what I'm going to present here. That's a deep learning over big data stacks. I believe is an emerging paradigm in the future. Actually, not only me, in the community, if you go to Spark or Hadoop Summit, a lot of people trying to do different kind of work to make this convergence happens. So for example, Caffe, SparkNet, TensorFlow, Spark, TensorFlow, Deep Learning 4J, Big Data, all these stacks currently can support the underlying Spark environment or Hadoop environment, okay? So this is happening. So if you look at DLoBD stacks, what happens actually is they have a lot of layers, okay? This actually is one of the major concerns people have for deep learning over big data stacks because people may think that is suboptimal performance. Because look, your application is here, then your high-performance networks or GPU is actually sitting here. Now the question is your application have to go through all these layers. Tell me how much benefit you can actually gain in the applications. Okay, many of the numbers we saw in many papers or talks actually in this layer. We run some point-to-point or bandwidth benchmarks here, but actually that's not enough. Okay, because we are here, application in here. You have to deliver your performance benefit, go through all this layer, come to this real application. Like as Dr. Harry mentioned, so this is actually happening. This kind of convergence is happening by the effort from all three different kind of communities. This is not just buzzwords. This is actually real solid work being done by a lot of researchers and developers. Let me give an example. Let me just go into this picture, okay? This is actually happening in 3 domains. So deep learning guys, they're trying to develop more and more or powerful, better models and some public data sets, okay? And also some deep learning libraries. And then big data guys, they're trying to develop a lot of new infrastructure, middlewares, like for example, in Apache community, a lot of new kind of framework being developed every day or every month, something like that. For example, today you're talking about Spark, tomorrow people may try to pick up Flink. A lot of things actually happen, right? And the HPC guys, like we are trying to develop a lot of powerful, high-performance building blocks, like MKL, CUDA-DNN, RDMA, GPU-direct RDMA. Now the question is how we really develop a stack which utilizes the knowledges from all the 3 domains, make them powerful and efficient. That's the goal of DLoBD. So with this, let me give some kind of case studies, what we have done in our group. Broadly, we have 3 different kind of categories. One is the traditional big data stacks, how we optimize it. Based on that, we also want to understand what kind of communication, computation, the I/O requirements of DLoBD stacks on top of big data stacks. So we give 4 examples. Okay, Caffe on Spark, TensorFlow on Spark, ML on Spark, which is CNTK on Spark, and then Big Deal, which is from Intel. So this will cover all different kind of popular DLoBD stacks these days available in the industry. And then finally, we'll give some kind of other case studies how we can optimize it. So like many of you may know, we have been working on high-performance big data project for the last 6 years. And we have a lot of different kind of packages available. For example, RDMA-based Apache Spark, RDMA-based Hadoop, not only for 2 series, 1 series, we are working on 3 series as well. And we also have plugins for Apache distribution, Hortonworks distribution, and Cloudera distribution. So no matter what kind of distribution you're using, we have plugin you download and apply it. You can get native RDMA support. And RDMA for Apache HBase, RDMA for Memcached. And then not only that, we also have a lot of benchmarks available because these days some people say how can get the numbers and understanding those numbers. So we have some benchmarks available as well. So not only that, actually, these days we also support OpenPower chips. And a lot of people talking about cloud. Now we are trying to support Singularity and the Docker in this stack. So tomorrow, because I will talk about the cloud, I will introduce something here, like how to run Hadoop on top of Singularity and get good performance with RDMA. So this is another curve. Dr. Harry mentioned the MRPG curve. This curve is like a high PD curve. So as you can see that we started 13, now it's 18. We have a lot of downloads happening. And because if you look at this different release, actually our goal is we are trying to develop a native RDMA-supported big data ecosystem. Okay. So we are hoping that all this big data framework can run on top of native RDMA networks directly. So here we just give 1 example. This is about Spark. So we have done this work from the very early version. Actually, the first one we worked is 0.7, but because of they evolve very fast. So the first paper we published in Hot 14 is 0.9.1, and over the years, Spark is being optimized heavily in the Spark core as well as new workloads. So today I'm going to talk about something here. So RDMA Spark and new workloads, DLoBD on top of Spark. So what we did for Spark basically is that, okay, in Spark in the backend, some of you are familiar about Spark programming. The core concept is about RDD. So in RDD, you have to develop your application with this core concept, and they propose some APIs called transformators and operators. So when the transformator has kind of wide dependency, basically it means you have to shuffle your data from parent RDD to child RDD. So that phase is very time consuming and network intensive. That's a good message for this group. So when they do shuffle and they do the network communication, there are 2 default approaches available inside Spark. One is based on Java NLL shuffle mechanism. The second one is based on NetT. Both of them are based on the default socket interface and libraries, and then running on top of Ethernet or IP over IP. And then we actually designed the RDMA backend and pluggable into the Spark core so that we can bypass the traditional communication flow and then take the communication flow directly on top of verbs. So with that, we are able to get a very good performance improvement. I will show that in the next slides. So currently, this package is actually available. We support 2.1.0 now. Almost the latest version is 2.3, I think, currently. And we support a lot of new features, including the open power support. So this package actually is also available in the PostCloud and the supercomputer. Here we give 2 examples. One is SDSC command. If you go there, if you have the account over there, you can directly modular load RDMA Spark, and then you can run. Okay. And then for the Chameleon Cloud, this is the NSF Supported Cloud. We have appliance, so you can go there and get the appliance and deploy your virtual machine automatically. So here is some example. We run the Intel high bench PageRank graph algorithms on top of RDMA Spark, as well as the IPOVD for the Spark. So as you can see that when we scale up to 1,536 cores, we are still able to get 43% performance improvement. That's very good improvement. So here I want to highlight that we don't change any hardware, we don't change any applications. We just bring the high performance communication protocol inside Spark, so you can get this kind of performance benefit. Okay, so that's something. What about the big data stacks on top of RDMA networks? The next important thing I want to highlight here is how to benchmarking and characterizing DLoBD stacks on RDMA networks. So before that, let me introduce some kind of methodologies. Okay, and also these days, many people trying to publish the numbers. Now the question is how you understand those numbers, whether those numbers make sense or not. For example, some people say that I can improve X times. Some people say I only improve 20%. So what's meant by those numbers? Okay, we have to have a good understanding of those numbers, and then you can convince your developer or your boss whether we have the investment or not. So basically, for this kind of benchmarking methodology, you have to choose good model and data sets. Okay, there's a lot of model available. I will give a table later. So, but broadly, this model has different kind of numbers of layers, and some model is very big, so basically very deep or very wide, and some model is very small. And then for data set, similar. Some data set is very small, like MNIST. Some data is very large, like ImageNet. Okay. So now the question is, if you combine the different model and different data sets together, what kind of performance you will get? And then the DLoBD stacks, of course, that's the major focus of this talk. So I choose Caffe on Spark, TensorFlow on Spark, and CNTK on Spark, and a big deal. And now all of these things can run on top of Yarn, and as well as HDFS. And then what kind of characteristic dimensions we are interested in? Here we want to show that comparison between CPU solutions and the GPU solutions, and the native RDMA solutions with IPOV solutions or other solutions. And then out-of-band communication pattern and in-band of communication. I will introduce what does it mean. And then the last important thing is you need to generate reasonable evaluation reports. There are different kind of ways to generate reports. You can say that what kind of performance for end-to-end training time, or time to reach a certain accuracy, or execution time for each epoch. Okay, and the scalability, resource utilization, and also breakdown. Okay, how much time spent on each of these layers. Now let me show you some kind of architecture overview of different stacks. The first one is about Caffe on Spark. So Caffe on Spark, the way how this application gets launched, or this framework gets launched, is that you need to define your deep learning application with Caffe and on Spark API, and then this application will get loaded by Spark driver. And then this driver will talk to the Yarn resource manager saying that I need some containers to run my job. Okay, the Yarn will allocate some resources for you. And then this resource get reserved for Spark, and then Spark will launch a Spark executor in this container. And then each executor will load the Caffe core into the Spark executor, and then this core will execute your Caffe algorithm. Okay, and then in the Spark and in the Caffe core, they will utilize either CPU or GPU based on your configuration. So after the computation is done, there's a modular called model synchronizer, which actually synchronizes the parameters and get a newer model, and then you go to another iteration. So HDFS was sitting here so that if you have any data like a model on your output, you can directly load from HDFS or write back to HDFS. This is how Caffe on Spark works. The second one, TensorFlow Spark. Similar kind of flow, but the difference is that TensorFlow by default uses primary server architecture. Okay. Today, many talks mention about deep learning, about or reduce or to all those kind of pattern. But there's another way, very popular, is primary server. Okay. Primary server basically means that you need to select one of the executor as a primary server instance. You can select one or multiple, depends on your configurations. And then you have multiple workers. And then this worker will transfer their parameters to the primary server and then get calculated in primary server, and then you get a newer model. So that's the way how TensorFlow works. That's called primary server-based architecture, okay? So similarly, they have RDMA or TCP/IP-based protocols, so you can use gRPC or gRPC plus X to accelerate your communication. That's about TensorFlow Spark. A third one is ML Spark, which is CNTK Spark. Same architecture. The only difference is this architecture is very similar to Cafeon Spark. The only difference is that for CNTK Spark, by default, they're using MPI to do the model synchronization. So that's why if you see the model synchronization part, they're using MPI to achieve TCP/IP-based or RDMA-based communication. Everything else is similar. Now let's go to Big Deal. Big Deal is why I want to show Big Deal here, because Big Deal is a totally different strategy, okay? Earlier 3 stacks, they always have their own or dedicated component to do the model synchronization, basically communication. That component actually bypasses default Spark shuffle architecture. Okay, so basically it means they have to do an out-of-band communication. But in Big Deal, Intel guys is trying to do a way in a different manner. So they are trying to integrate deep learning jobs, deep learning capabilities with Spark in a tight coupled manner. So they are kind of use block manager which inside Spark core as a primary server or distributed primary server. Okay, so that all model synchronization can directly happening by Spark help. So that's a very different kind of design philosophy. So we call this kind of things strategy in-band communication. Okay, so with that, whatever we mentioned earlier, like if you do some kind of optimization inside Spark, like RDMA-based Spark, this can be directly benefit for this kind for Big Deal workloads. Okay, so this is like a high-level overview of 4 different kind of stacks, how they work on top of big data stacks. Now the question is, what kind of benchmarks and data set you can select to evaluate with these stacks? Like I mentioned, there are a lot of different kind of models available and the data sets available. You can, for example, you can run I think this is MNIST, CIFAR10, and ImageNet. Okay, and then for model-wise, you can select AnnexNet, Sigmoid, and the VGG, AnnexNet, GoogleNet, and ResNet, those kind of things. And each of these models have different kind of layers of convolution layer or for connected layers. Now let's take a look at some of these numbers. Let's say if you run some of this model on top of Cafeon Spark first. So here is no RDMA. We just want to see how Cafeon Spark can take advantage CPU or GPUs. So all of this actually running on top of IPOB protocol. So let's see, we scale number of nodes and also basically number of GPUs from 1 to 16. So we can see that with different kind of solutions like CPU plus OpenBLAS, CPU plus MKL, or GPU plus CUDA-DNN. Okay, we see that in many cases CUDA-DNN is able to reduce the execution time significantly, almost 90% performance improvement. But this doesn't mean GPU always win. Okay, for example, if you look at this side, actually for this case, the CPU plus MKL can show the best performance. That's pretty interesting. So this means that actually, if you don't have GPU, you have some kind of Intel chips or KNL. Actually, you can say that I can also do very good deep learning jobs. But if you have GPUs with CUDA-DNN, you can also get very good performance improvement in your platforms. That's about the CPU and the GPU comparison. Now the more interesting thing is based on that study. Actually, we find when you scale to more nodes, the performance is not going to better. Actually, sometimes the performance is going bad. For example, if you see here, 8 nodes and 16 nodes, same computation tasks, but time actually getting increased. This obviously means that communication becomes a bottleneck at that time. So this is good news for this community because it means RDMA based networks or high-performance networks can help for deep learning applications. That was actually we compare some models with Convergence Spark and TensorFlow Spark. This is, I think this compared with IPLB and RDMA protocols. As we can see that for some cases, RDMA can achieve very good performance improvement, like 45% improvement or 51% improvement. Okay, that's very good performance speed up. And then but for some cases, we don't see too much differences. For example, like TensorFlow on Spark, we only see like 5% differences. How to understand these numbers? Okay, so this basically means that sometimes your model may be small or your data is small. You don't need that much high performance bandwidth, high speed networks. The IPLB protocol with some network speed may be enough for that case. But if you really go to real scenarios, you have large, huge data, you have huge model, then RDMA networks definitely help for that. For example, for this case, okay? Now, for CNDK, similarly, we run, because this was based on MPA solutions. So we want to see whether there's different kind of performance characteristics. We see that interesting GPU plus CUDA-DN. Oh, here there's no GPU solution scheme because by default, CNDK only supports CUDA-DN based solution. So here we see that CNDK has very good optimization with CUDA-DN. So it shows around 55x faster performance than CUDA plus OpenPlus, and then 15x performance speed up when you compare it with when you run CPU plus kernel. And then for CFAR10 and CFAR10 Quick, this model RDMA and IPLB look similar. Again, the main reason is because of IPLB. For this case, IPLB with EDR is able to deliver sufficient bandwidth to the model training. So this is about end-to-end training performance. Okay, this is one way to present your numbers. But many deep learning guys actually they don't want to see those numbers because those numbers are kind of for system researchers or for HPC guys. But many of them are actually very interested with another way, kind of. Can you show me the time for my application reach to a certain accuracy? Let's say 70% accuracy. Okay, that's actually very different than the training. If you just fix number of epochs and then show you the end-to-end training time. So here we actually show 3 graphs. The first one is Convergence Spark. This one is Convergence Spark with GoogleNet. This one AlexNet, and then this big deal with CFAR10. So as we can see that if we show the time which reach 70% accuracy, okay, RDMA give you like 22% improvement, 15% improvement, or 48% improvement, depends on your model. Okay, but later on I can show you some tricks which I can give you much better performance numbers, like a 2x performance improvement, something like that. So this basically means if you want to show numbers like a reach to some certain accuracy, the number actually looks a little bit small, like 20% or 50%, something like that. Okay, another perspective is like a memory utilization and the network utilization. Here, what do we see that no matter what model you're training or data set you're training, what we see is that the GPU memory and the host memory actually is not fully utilized for some reasons. And also network bandwidth, for example, for this case, even for RDMA, they only achieved around 25 megabytes per second, but actually you have like 100 Gbps bandwidth, right? So this actually means a lot of room, big room for us, for this community to continue improve the performance and the efficiency. So another interesting perspective I want to present here is that when you run your jobs on top of DLoBD stacks, there are a lot of layers like I mentioned earlier. Now the question is, can you tell me how much time spent on each of these layers? Where is the bottleneck? Okay, should we optimize this layer or that layer? Should we optimize computation, or I/O perspective? Okay, so here we just did one example providing. So we run the TensorFlow Spark and the native TensorFlow. Okay, TensorFlow Spark means you run TensorFlow and then Spark and then YARN and then HDFS. Native TensorFlow basically means you note everything from your local file system and then do the trading in TensorFlow space, and then you get everything. So as you can see that the training time almost similar to the actual training time, but with TensorFlow Spark, you need to spend around 15% of the time in the Hadoop YARN scheduler layer. So basically, you need 15% of time to allocate containers, get those kind of things set up. And then again, you need another 18% of time spent on Spark layer, which basically initialize your Spark context, launch your jobs, and then and then construct those RDD and do those kind of things. So basically, this is good news or bad news. Okay, good news basically means that, okay, good, we have a job to optimize it. Bad news, but also bad news, you need to put a lot of effort. But another good news is that we probably can optimize a lot of things with native RDMA support. We want to bring down this overhead and show almost near to native performance. So later on, I will show why here RDMA and IPLB look similar. Again, this is the default TensorFlow. So default TensorFlow has IPLB protocol support and as well as the RDMA channel you can run with native verbs. So again, this part I want to summary a little bit because so many numbers. The major information is that the RDMA protocol can show good performance improvement as if your model is big or your data is big. Okay, so sometimes we see around 2.6x performance speed up, but sometimes your number may be only 20%. That totally depends on the way how you present your number. So, but again, there's a large room to further improve the DLoBD stack, like I mentioned earlier. There's so many bottlenecks, and the resource utility is not very efficient, actually. And we also find out that we need a lot of more benchmarks and data sets and tools to analyze all these things. We did these things by our knowledge, but actually, we see a lack of tools to get all this information. So last of this talk, I want to present some kind of acceleration case studies. So like I mentioned earlier, we did RDMA-based Spark, right? We show some good performance improvement for PageRank, those kind of graph computing algorithms, but that's not a big deal. The big deal of this talk is about Big Deal. So Big Deal is the Intel solution, which is running on top of RDMA Spark. But like I mentioned, it is using the in-band communication, so it can utilize our RDMA-based Spark by default with just some kind of configuration changes. So here, I just want to show you another way of presenting numbers. So this means the x-axis means epoch number. So around 1, 2, 3, until 20 epochs. For each epoch, I can report a number. And then here is accuracy, how much accuracy are achieved across these epochs. And then, as we can see that if we just show epoch time, then we can show you around 2.6x performance improvement. But actually, earlier, do you remember, if we show that the time you reach the certain accuracy for Big Deal, I can show you around 40% improvement. So anyway, RDMA can give you much better performance improvement in both of these metrics. And then another way to show is scalability. So basically, if you increase number of CPU cores, because Big Deal is running on top of CPU, not GPU. So whether you can scale your application. So here we compare with IPLB and the RDMA. We see that RDMA has a very good curve, looks very smooth. And if you look at the numbers, actually, for some point, you can improve 2.6. You can achieve 2.7x speed up. So the last story is about TensorFlow. So for some of you, if you're not familiar about low-layer stuff about TensorFlow, so here's a picture of how TensorFlow organized. So like I mentioned earlier, you have your job is here, and then you have a master. This master will launch the TensorFlow infrastructure. So in TensorFlow, you will specify how many primary servers you want. So let's say here we have one primary server, and then we have one worker or multiple workers. So this worker will do the computation and then transfer the models to the primary server. Okay, the way how they transfer parameters is based on the gRPC protocol. Or like I mentioned, gRPC plus X. X basically means you can run gRPC with the verbs. It's available in the TensorFlow package. Or you run gRPC with MPI. Okay. Or you can have other contributors which develop some other schemes. So what we see is that in all these available channels, we see their protocol is very static. They only have one protocol available, or the design is not very efficient. We actually have a paper to analyze all those kind of bottlenecks, which is under review. So we just want to show some numbers here. So our design native RDMA-based gRPC compared with gRPC over IP over B, we are able to achieve almost 2x or 3x performance speed up, no matter what kind of message size. Like Dr. Hari mentioned earlier, for deep learning workloads, a lot of large message transfers. Okay. In the meantime, there was some small and medium for some administrative tasks. So our design can show almost 3x speed up no matter what kind of message you are going to transfer. So this graph actually shows you very interesting results about ResNet with different kind of batch size and different number of nodes. We compare with gRPC, gRPC plus VERBs, gRPC plus MPI, and our gRPC plus RDMA. So we can see that for small batch size, of course, you have more complication, okay? Because you basically, essentially reduce the local computation, okay? So for small batch size, you show very good performance improvement, like 40 or 30 to 40% improvement. But again, for large batch size like 64, we still see around 20 to 30% improvement. That's for ResNet. And for Inception 3, similarly, we see also around 30% improvement for small batch size, 20 to 20% improvement for small batch size, for large batch size. So let me, because of time, let me conclude this talk. So basically, we discussed some of the challenges to design next generation efficient deep learning stacks on top of big data. So the major idea is we are trying to unify these stacks, become a unified system, so you don't have to have multiple clusters. You only need one cluster to handle all the pipeline or workflow in the first slides I mentioned. So some of these results very promising, again, but also related with your workloads, like I mentioned earlier. And also there's some different ways to present your numbers. So when you get the numbers, you need to understand what those numbers mean, actually. So with this, actually, we also organize a workshop in IPTBS with some of you from academia or industry want to join IPTBS. Feel free to come to our workshop. We have actually a very exciting panel, which we are going to discuss which framework is the best for high-performance deep learning, big data frameworks or HPC frameworks. So again, in this week, we have another two more presentations. One is about the cloud, one is about NVM and RDMA. So with this, let me thanks for your attention. I'm happy to take any questions.
We don't have time for questions, so maybe you can talk off.
Okay, sure. Mm-hmm.